Hi everyone, I'm Libo and today I'm excited to share our recent work. This research sits at the intersection of privacy protection and language modeling with the goal of generating de-identified medical records to expand training datasets and help address issues like data imbalance in the clinical domain. The talk will be organized into four main parts: motivation, methodology, results, and conclusion. So let's begin with the first part, motivation. Accessing real medical records is becoming increasingly difficult, which poses significant challenges for both clinical education and AI models development in healthcare. While some public datasets like MIMIC and I2B2 do provide de-identified records, they are typically limited to specific institutions or regions, small in scale, and often focused on narrow patient populations. As a result, these datasets tend to overrepresent certain subgroups while lacking diversity in others, leading to biased models and poor generalization. To address these issues, we aim to generate de-identified clinical records that are more diverse, stable, and privacy-preserving. Most existing work in this space have relied on carrier language models, including decoder-array models like GPT and encoder-decoder models like T5. In contrast, masked language models offer key advantages. Their bi-directional architecture enables richer contextual understanding, which helps reduce structural inconsistency, semantic drift, and hallucinations in generating text. In our study, we explore an MLM-based mask generation approach, incorporating a de-identification model using filter, which is a rule-based tool that identifies and removes protecting health information without requiring any annotated labels. Our goal is to generate synthetic medical records that strike a balance between fidelity, retaining clinical meaningful information, and privacy. By leveraging different masking strategies to control this trade-off. Now let's move on to the methodology. Our system have two main components. You can see them in the figure. On the left, we have the masker, and on the right, the masking filling system. Basically, the masker decides what to hide from the input medical records, and then the masking filling model fills in the blanks to generate a complete static version. Let's break down the masker, which works in three stages. First, we apply the identification using a tool called filter. It removes sensitive elements like names, IDs, and addresses. And this best part is, it works without any manual labeling. Filter achieves over 99% recall when it was first evaluated, so we're integrating it into our system directly. For typical DID tasks, high precision is important. You don't want to accidentally delete too much non-sensitive information. But in our case, removing extra content is actually okay. It introduces some variability, which is helpful for generating diverse outputs. What really matters is not missing any sensitive information. So we don't care too much about the precision of the identification tools. Secondly, we keep important medical contents using a medical named entity recognizer with some style. Based on the I2B2 2010 dataset, it identifies key entities like problem, test, and treatment. These are preserved to make sure the clinical meaning stays intact. In the future, we may experiment with replacing some of them with explanations to enhance readability or simply the text. Thirdly, We use a part-of-speech tagger, also from Steza, developed at Stanford. It tags on the remaining words and we randomly mask tokens based on their part of speech. For instance, setting a noun ratio of 0.5 means half of all nouns will be masked and later predicted. This allows for fine-grained control over the variation introduced. Now let's talk about the masking feeling system, which has two parts, the MLM model and the feeling algorithm. We use bioclinical BERT, a pre-trained medical language model based on BERT. Giving a sentence with masked tokens, it predicts likely replacements, and we use these predictions to complete the text. For the mask filling algorithm, we ask two questions: which token do we select and how do we apply it? We explain two strategies: simultaneous chalk filling, where all the masked tokens in the chalk are predicted at once by the model, and iterative mask filling, where tokens are filled one by one, with the context updated after prediction. This improves contextual consistency and output diversity, though it's a bit more time-consuming. As for selecting the final predict word, we consider two options. One is deterministic, where we simply pick the word with the highest probability, and the other is stochastic, where we sample from the full probability distribution. In our case, we chose the statistic approach because we wanted to ensure enough variation in the generated records. Based on the system we just described, we conducted experiments using the I2V2 2014 datasets, which provides gold standard PHI annotations for the identification test. We split the training and validation sets with a fixed 18-20 ratio. Then we tested 4 system configurations as shown in the table. In all settings, we masked all PHI entities but kept the medical entities extracted by the NER model. By the way, the ratio is something we plan to explore further in future work. The first 2 configurations using simultaneous chalk filling with post-masking ratio of 15% and 17% respectively. The last 2 iterative mask filling with post-masking ratio increased to 17 to 19%. Throughout the experiments, our main evaluation metrics were perplexity, which reflects how confident the language model is in predicting masked words. After identifying the best performing configuration, we retrieve the model using the entire dataset, both the training and validation portions, to finalize the synthetic generation setup. This allowed us to examine how the masking ratio and filling strategy influence performance. We evaluated our system from 3 perspectives, also as shown in the table. Lexical similarity measures how close the static text is to the real one, both in meaning and readability. We use Roche BERT score and readability metrics like flash rate ease, FKG, and SMART. For data utility, we tested whether the static records could support a downstream NER tasks, comparing performance to real data. The last one is privacy. We compared our output with gold standard PHI annotations, measuring how effectively sensitive information was removed and whether any of it appeared during generation. Okay, that's all for our methodology and experimental setup. Now let's move on to the results. Overall, our findings show that higher mask ratio help improve diversity in the generating text, though they do slightly reduce lexical similarity to the original, which is expected. Interestingly, we also observed that higher mask ratios actually led to better F1 scores in the downstream NR task. We believe this is because more masking introduces more variation, which in turn helps the model generalize better. In other words, it's often more beneficial to expose the model to 100 different sentence patterns that include 19 useful clues, rather than just 10 perfectly preserved sentences. That's also why, when we augmented the datasets by a factor of 2, the F1 score significantly improved from 0.827 to 0.836 in our first system setting. As expected, the iterative filling strategy consistently outperformed the simultaneous one, both in terms of text similarity and NR text formats. We also found that static records tend to have similar language, which led to higher readability scores compared to the original clinical note. And finally, most importantly, we were able to maintain a high level of privacy, a de-identification recall of over 0.9 and a very low re-identification rate of just 0.035. To sum up, our research can generate static medical records, including discharge summaries, admission notes, and doctor correspondence that retain core clinical meaning while introducing controlled diversity. Thanks to the flexibility of our masking and filling strategies, we were able to adjust the balance between fidelity and variability based on different application needs. We also demonstrate that static text is effectively in downstream tasks, achieving an F1 score of 0.836, which is very close to the performance achieved using the real data. Most importantly, we ensure strong privacy protection with a de-identification recall above 0.9 and a re-identification rate as low as 0.035. However, the system still have some limitations. For example, it may struggle with temporal consistency, such as maintaining coherent timelines across events, and might not always preserve the structure of interconnecting entities. Moving forward, we plan to explore logic-driven components to enhance coherence, try out alternative AI models, and adapt our system to new clinical domains such as oncology or radiology. Before I add, I'd like to briefly acknowledge the funding bodies and collaborators who supported this work, including UPRI, EPSRC, the European Union Horizon Program, and our colleagues involved in the 4D Picture project. Their support made the research possible. And with that, thank you for your attention, and we are happy to take any questions.